go through is we kind of like talk about the models. So first we talk about the performance matrix, like what are the performance matrix for the adsorbent materials, and why pure gases we need it, because usually in industrial scale we never see pure gases. Why we need pure gas adsorption isotherms? But here why we kind of like trying to explore the pure gas adsorption isotherms, and then this the models, pure gas adsorption isotherm models, and how to actually measure it. One way is applying the experimental techniques, one way is through simulations. How can we measure the pure gas adsorption isotherms or mixed gas adsorption isotherms? So these are the things which we will be covering in the second part. Okay. So these are the two things which we always look for. So one is the equilibrium adsorption capacity, one is the separation coefficient. Right? Whenever we look for a material, we kind of like look into the two performance metrics. One is the what is the equilibrium adsorption capacity, that means that how much it can hold for, right? How much it can uptake. And second one is what is the separation coefficient, right? That means that with respect to the other gases, so how much it can absorb. So that means that like when you say the first one, you can say it absorbs 100 kilograms. So that is a very high number, but it also absorbs 100 kilograms of other gas, you will not get any separation factor, right? So these are the two things which we always look for. So one is the adsorption capacity, one is the separation factor. Okay. So before exploring this one, we kind of like just go through the same process, again everything is same. Okay. How these adsorption isotherms are affected, right? So one thing why we kind of like try to explore the pure gas adsorption isotherms, right? Why we need pure gas adsorption isotherms? Because anyhow we are separating two gases, two or more gases. So why we kind of like try to explore pure gas adsorption isotherms all the time? First thing, we kind of like try to get the information about the porosity, pores, and when there is only one gas, how it is behaving. Right? So we kind of like try to get the ideal information. Okay, in ideal case, what is happening? How much it can absorb, right? First thing. Second thing is that once we know the pure gas adsorption isotherms, we can always predict the multi-gas adsorption isotherms based on the pure gas things with some assumptions, obviously, right? So this is the reason why we kind of like try to see what is the pure gas adsorption isotherms all the time. And once it is done, we kind of like go for the multi-gas. Second thing is that multi-gas absorption is always difficult to conduct. Experimentally, it is always difficult to kind of like get the multi-gas adsorption isotherms. So it is super expensive. So therefore, what we can do is like one of the cheapest way is like try to explore the pure gas adsorption isotherms and use it to predict the multi-gas adsorption isotherms. Okay. So how temperature affects the adsorption? So we will not get into the why adsorption is exothermic process, which we will see tomorrow. Whenever we say heats are involved, temperature is involved, we will deal with tomorrow. But for the sake of discussion, we start with, because adsorption is an exothermic process. That means that whenever adsorption happens, heat releases, right? So temperature significantly play a role in adsorption. So temperature will not play a role in absorption, AB. It will play only in adsorption. So what Le-Chatelier principle says? So whenever you deal with an exothermic process, right? So at higher temperature favors a condition that evolves less heat. When adsorption happens, heat evolves. Le-Chatelier principle says for an exothermic process, high temperature favors evolve of less heat. If you have to evolve the less heat, it has to absorb the less amount. So that's why as the temperature increases, adsorption isotherms, you see the adsorption capacity decreases. So usually that's why adsorption usually happens at room temperature, not at higher temperature. Okay. So that's what you can see, as the temperature increases at the same pressure, the adsorption capacity decreases. Okay. So yeah, so this hysteresis I think we kind of like discussed. So whenever always remember the point that whenever there is a capillary condensation, there exists a loop. So that is because of the capillary condensation. That's only one thing you have to remember. But yeah, we go for Langmuir adsorption residual. So we try to see when we kind of like discuss the isoderms, types of different isoderms, right? We try to understand what kind of mechanisms may happen based on the curve type. But we now kind of like try to build an theory what is exactly happening on an isotherm. Okay, so these are like theories. So when I say Langmuir adsorption isotherm, it's a theory. It has several assumptions, and based on the assumptions, they built a theory, right? So this Langmuir adsorption theory is based on the kinetic point of view. You all know kinetic theory of gases, right? So based on the kinetic theory of gases, they kind of like build this theory. So what are the assumptions, right? So they assume that in Langmuir theory, the surface is flat, right? So maybe it's inside pore or maybe exactly on the surface. The surface is always flat, something like this. And on the surface you have sides which can accommodate the gas molecules. They can accommodate only one gas molecule at a time. It cannot adsorb more than one gas molecule. So it actually is, because we say all the sides, this is all sides which can actually accommodate the gas molecules, they are energetically same. So that means that when a gas molecule comes from the gas phase, it may go to the any site with equal probability. Okay, so now you have a surface something like this. So a gas molecule is coming from the gas phase and trying to adsorb on one of the side here, right? So what is the rate of striking a gas molecule when it comes from a gas phase and striking a surface? What is the rate of striking based on the kinetic theory of gases? Remember? So that's anyhow, that will come back. So it actually go with something like this. So it depends on the mass of the molecule, temperature, on the pressure. So this is the rate of striking. That means that the gas molecule which comes here, it may adsorb or it may go back. So it's nothing to do with adsorption. It's like kinetic theory of gases. It does not talk about actual adsorption. It only says, okay, so when a gas molecule is kind of like flowing, it kind of like on a flat surface. So the rate of striking is given by this one, right? That's the pressure 2m kBT. So this is kind of like collision theory, which we kind of like call. It collides and goes. So that is the rate of striking, all right? It depends on all these parameters, temperature, mass, and so on. Say for example, a gas molecule comes here and strikes and goes back, comes here, strikes and goes back, comes here, strikes and goes back. And some molecule may comes here, hit at this site and adsorbs. And it kind of like sticks to the surface. Okay, so this rate of adsorption, which we kind of like write RA, so this is rate of striking. That means it's directly coming from kinetic theory of gases. So then rate of adsorption, maybe we kind of like put another column called alpha. This alpha actually talks about if this molecule is striking the surface 10 times, maybe out of 10 times, 2 times it may adsorb on the surface. It talks about fractional number of molecules that adsorb onto the surface after each strike, right? So this alpha talks about the fractional. So that's why Rs is replaced by Ra. This is called rate of adsorption. That means that like 10 molecules are colliding with the surface. Out of 10, only 20% is adsorbing. That alpha is 0.2. So this becomes rate of adsorption. So this may be true for the first molecule. So the first molecule comes and sit here. But what about the second molecule? Because it's already filled, the second molecule cannot come and sit here. So it will only can sit in the other places. So the second one, the rate of adsorption is P alpha square root of 2 mass times KBT. KB is Boltzmann constant and T is temperature times 1 minus theta. So theta is fractionally occupied. This is the total, this theta, which we kind of like call something like this. So this is the total number of sites, and this is occupied sites. So this is the remaining. So this is the fractional occupied sites. So 1 minus theta is the available sites, right? So this is, you kind of call it as now, like although I said in terms of volume, but you can call it in terms of sites also. Say for example, you have 100 sites, out of which 20 is already full. So alpha becomes 20 by 100. So 1 minus alpha is the available sites. Sorry, 1 minus theta, sorry. So that's where, so that is the rate of adsorption. So I'm just writing that one. Rate of adsorption is equivalent to P is pressure, alpha, which is number of successful strikes, and then this one. So what about rate of desorption? So to desorb a molecule, it requires some energy, right? Because whenever a molecule come and adsorb, we said that it's an exothermic process, it releases some heat. To send this one back, we again have to supply some energy. So it's we need some energy. So maybe that's an activated process that we can kind of like deal with Kd, which is an equilibrium constant, times, we write it as theta because only theta number of sites are full. So any molecule can go back. So this is rate of adsorption and this is rate of desorption. At equilibrium, rate of adsorption is equivalent to rate of desorption. You kind of like equate these two things. Right. So this is rate of adsorption. KBT, oh pi is missing all the time, shit, okay. KD theta. Because this is an activated process, you can kind of like write. Something like that. Because this is rate constant. It's an activated process. So this is whenever you write, right, anything you can write, like for example diffusivity also you can write for all activated process. Something like this. On the similar lines, Kd you can write, this is the rate of desorption that corresponds to the infinite temperature exponential of minus Ed. So this is activation energy for the desorption, that is equivalent to the heat of desorption, RT times theta. So we just kind of like rearrange this one. what you get is something like this. Theta is equivalent to Kp over 1 plus Kp, where K is a constant which will take care of all the terms available here. Either you say this one and yeah, this one, everything will go into the K. So I don't know whether I have this one. Yeah. So this is the fundamental basis for Langmuir adsorption isotherm. Any questions here? What you just have to do is like, you know, this is equivalent to this. You just arrange everything into this form. Theta, you have thetas here, and you have pressure here, and everything else is constant, which is K. That's it. You'll get a form something like this. Right, so this K depends on the temperature. So at different temperatures you will get different Ks. All good? So this is the basis for Langmuir adsorption isotherm. So as we see, this all depends on the basis of assumptions which we make here. The assumption is that the surface is flat. The second one is that all adsorption sites have equal energy and only one molecule can adsorb at one site. So that's why this only applicable to monolayer adsorption. We never talk about multi-layer adsorption. Okay. So therefore, whenever you try to fit a adsorption isotherm.
So there is one question from online participant. Does this mean the lighter molecule will always adsorb faster or more? Rate of adsorption is inversely proportional to mass.
Rate of adsorption is inversely proportional to the mass, right? Lighter molecule?
Yes, the question is, does this mean the lighter molecule will always adsorb faster and more? Faster
more we
or
cannot
more?
say, faster we can say, right? So more or not depends on adsorption and desorption, both the things together. Faster, yes, because it actually, like lighter molecule diffuses faster. That means that it can make more number of collisions with the surface. So it's like more chance that it will try to hit the activate sites and sit. That is yes, but the second one is not correct. So that depends on several characteristics, right? So it's only rate of adsorption. It's nothing to do with the equilibrium adsorption. Yeah.
Okay, fine.
Yeah, that's it. Yeah. Yeah. So as I said, this is only applicable to monolayer adsorption when the surface is flat, and it has, like, you will never find like a surface which is really flat, and so that's why it has like so many limitations, but we will kind of like come up with other models. But before going to that, whenever we try to fit a isotherm with Langmuir adsorption isotherm, what we do is we kind of like try to readjust things, right? Like what we do, theta is V over Vm. Vm is the total monolayer volume and V is the actual volume. So we kind of like try to rearrange in such a way that 1 over V is equivalent to 1 over Bp Vm over plus 1 plus Vm, and we try to plot 1 over V versus 1 over P, like y is equivalent to mxc form. So this is y here and 1 over P is x. So that's what you see, 1 over P versus 1 over V. So where the intercept is 1 over Vm and the slope of the line is 1 over B. So whenever you get the adsorption isotherm data, you try to plot 1 over P versus 1 over V and see if it is a straight line or not. If it is a straight line, it follows Langmuir adsorption isotherm. If it is not, it does not follow. Okay. So therefore, because Langmuir adsorption isotherm is so ideal, it only talks about monolayer adsorption and then flat surface. they come up with friendly adsorption isotherm. Initially when it started, it has no fundamental basis, right? So unlike Langmuir adsorption isotherm, it does not have any fundamental basis. It kind of like try to fit with a polynomial equation. Whenever you get an adsorption isotherm, you try to fit within a polynomial equation. So the polynomial factor will change. So it will have something like that. Q is the adsorption capacity, K is a constant, P is the pressure, and M is a constant. So here we have two constants, K and M. Both are depends on the temperature only and changes with the system to system. Okay. So, although I don't have something here, but I can tell you one small thing. Right. So whenever you kind of like try to plot a friendly adsorption isotherm, right? So what you have on the x-axis is the pressure, what you have on the y-axis is the Q, right? So when, because we said that M and K are constants, now you just play around with M. Let's go with M is equivalent to 1, so then it's a straight linear equation, something like this. Q is equivalent to Kp, so the slope is K, right? So as the M value increases, the non-linearity goes. So like say for example, M is equivalent to 2, it goes something like this, right? So like that if you try to do at home, when M is equivalent to 10, right, it goes like a rectangle. So is this value increases suddenly, and then goes like this. This may be corresponding to M is equivalent to 10. Say M is equivalent to 3, something like that. So usually whenever we try to fit with friendly adsorption isotherm, M is between 1 and 5. If it is higher than 5 or bigger than, like larger than 5, so there is something wrong, we have to see. What we say is that when M is equivalent to 10, this adsorption isotherm is kind of like called irreversible adsorption isotherm. This only happens when the process is irreversible. It follows a rectangular kind of curve. That's what we see. Okay. I think we are running late. Oh. Okay, so the next one is the BET adsorption isotherm. So here we have like 3 others. So this BET adsorption isotherm is actually started by Professor Brunner. So one you see on the one. So Professor Brunner kind of like started kind of like building BET adsorption isotherm on the basis of Langmuir adsorption isotherm. It actually follows all the assumptions of Langmuir adsorption isotherm, but it actually includes the fact that it also allows multi-layer adsorption. Okay. So what he said is that in his assumptions, everything else is same. Whatever we did for the Langmuir adsorption isotherm, similar derivation we have to do for BET. But the only difference here is that on the first layer, gas molecules will adsorb on the surface. On the second layer, the gas molecules will adsorb on the gas molecules. So here you will see the rate of condensation. So that means that gas molecules will come and sit another gas molecules that forms like a liquid-like structure. So and then on the top layer of the gas molecules are interacting with the gas phase. So these are the 3 things which he kind of like incorporated into the system and come up with the BET adsorption isotherm, which we will not go into everything. Yeah, it kind of like has a structure like something like this. Theta, which is V over Vm, that is whenever you see theta, that we call it as fractional coverage, and C is a constant, and zeta here is P over P naught. P is the pressure and P naught is the saturation pressure. So there are only 2 constants, which is C Like there is only one constant actually, C, and then another one comes here, P naught for a given system, right? So this BET adsorption isotherm typically used to compute the surface area. So because it kind of like deals with the multi-layer as well, so it is useful to compute the surface areas. So if you just rearrange this one, what you see usually is that what you just need to do is that in place of each zeta, you just substitute P over P naught and then just rearrange that equation. You will get something like this. So what you have is the pressure here, this is the total volume, it's P naught minus P, this is the saturation pressure, this is the actual pressure, and V over Vm, which is monolayer volume, C is the like whatever you say Q, or C the concentration, and everything else. Oops, sorry. I think that's C. Got a lot of confusion, but okay, leave it. That's not. So we talk about several isotherms, but okay. Okay. So we talk about different adsorption isotherms, right? So and then different models, but actually experimentally how we measure it, right? What is the procedure to calculate the adsorption isotherms, right? How we will actually measure it. So there are several methods available, but most likely we follow these two methods. One is the volumetric method, one is the gravimetric method. So we will actually go through each method and see how each method works, right? So let's start with volumetric method. Right. So this is the simple thing, but we kind of like see how we do it in reality, right? What we will do it, the principle here is that we measure the volume of the gas adsorbed by a solid adsorbent, right? That is the principle overall. How we do it, we'll do, but this is the procedure. What we have to do, we need to place the adsorbent material in a chamber and introduce the gas and measure the pressure changes. After equilibrium is reached, record the final pressure, and yeah. So this method is suitable for the gases. That means that we cannot use it for the liquids. I will tell you why. And second thing is that this method is very quick than gravimetric method. Gravimetric method usually takes a lot of time to predict the gas adsorption. Okay. Let me see what I have. Okay, so this is a flow diagram, right? What you can see here, right? So although it's shown for the example of hydrogen, but it can be any gas. So the gas enters from here. You have a wall, and then you have a manometer which measures the pressure. So then, yeah. So here we have two chambers. So this is chamber 1 and this is chamber 2. So we know the volumes of both these two chambers. We know V1, we know V2. So how we start is that whenever we try to calculate the gas adsorption, we try to close valve A, right? So initially we close the valve A, so that means that no gas is coming up, and then try to evacuate everything which is there in V1 and V2, right? So we open valve C and discharge everything through B, okay. So then this V1 and V2 is empty, only solid material is there, okay. So now you close C and B, that means you close this valve C and then also valve B. So that means that here you just remove the connection, this closed, and open valve A. So then what happens, the gas that enters goes into the chamber V1, right? That's perfect. Right? So because this is a gas, ideal gas law is applicable, which is PV is equivalent to nRT. So the number of moles of gas which is in the chamber 1 is equivalent to P, is the known pressure, V1 which is the volume here, right, capital V, RT which is, R is gas constant, T is anyhow the temperature which we are maintaining. Okay. So this is the initial number of moles, right? So then what we do, now we also close valve A. Once it fills all V1, we filled everything, then we will close valve A, right? And then only open valve C. So that means whatever gas is there here in this region can flow to this region. Okay. So this gas now is expected to right. So from here we can change in number of moles. Sorry, yes, pressure also changes. It's all at the same temperature. So you got it? So what happens? Initially we kind of like fill the V1 chamber with the gas. So that means we know how many number of moles of gas is there, right? So then we open the valve C by closing valve A. So valve A is closed, valve B is closed, right? So this is also a valve. You just like, this seems like this is a valve, right? It's like comes in this way. Okay. So we closed valve A and valve B so that the gas can go from valve 1 to, so like region 1 to region 2. And then we measure the pressure again, right? So that is the second pressure, P2. And it occupies two volumes, V1 plus V2, right? So then you try to find out the difference between NF minus NI. If it does not absorb anything in the solid system, these two should be same. If it absorbs, the difference will come here, which is NF minus NI. So that means this minus this. Okay. So that's why we call it as a volumetric method, which we kind of like try to measure the changes in the pressure, right? You got it or no? What we do first? We try to close valve A and C, or like that doesn't matter. Even like you start with, we close valve A, valve B and C is open, and we try to evacuate everything from here. So that means that these two chambers are initially empty. Then we close valve B and valve C and open valve A. Whatever gas enters will go into chamber V1, which we know the volume. So that is the initial number of moles. N1 is equivalent to P1 V1 over RT. How you will know the P1? You close valve B, you close valve C. So here you have manometer, it can measure what is the pressure inside the system. Okay, fine. Once that is done, now you also close valve A and open valve C. So the gas can flow between these two regions. And finally you measure the final pressure, and the volume is V1 plus V2. So which is V1 plus V2 RT, right? If gas molecule does not absorb into the solid, these two are same because the same gas is there. If it absorbs, you will see a difference here. So this is the amount absorbed, right? That you have to do for each pressure. You start with initial pressure and then you have to do it. So this is volumetric method.
Assumes that the temperature of V1 and V2 is same,
Yes,
which may
that's
not
why
be the case all the time.
Yes,
Because
that's why
your
we have
V1
thermostat.
is not immersed in the bath.
No, we have a thermostat or bath here,
Yeah.
which kind of like always maintains the temperature.
That maintains the temperature of V2 only, not
No, it
V1.
maintains the temperature of the whole system.
Both system?
Means
Okay.
V1 plus V2.
Okay.
Yeah, we always maintain at the same temperature. Yeah. Because gas is allowed to move from one region to another region, obviously it will come into equilibrium. So, right? Dead volume, we kind of like try to fix it in the first stage when we do the initial thing, and then that we will use it for all the cases. Right? So this method is simple, straightforward, but as I said, we assume that the gas follows the ideal gas law. We may not directly apply everything to the liquids. Right? That's why when we kind of like discuss this one here, we said like it's suitable for the gases. Otherwise, we have to, still we can apply, but we have to apply the corrections and everything. So people do it, but it's mostly suitable for the gases. Yeah. Okay. So the next one is gravimetric method, which is simple. Here we no need to do anything. So the system will do everything for us. So it's a very sophisticated system. It actually involves the measurement of the change in the mass, right? You first initially you have the solid material, so you measure it, do the gas adsorption, again measure the weight. The difference in weight is equivalent to this one. But how we measure is the thing. Oh yeah, I think, oh shit, some equation got missed, but it's fine. So, yeah. So here what we should see is that the amount adsorbed is equivalent to, yeah, M2 minus M1. So M1 is the initial mass of the solid. M2 is the after adsorption happens, mass plus gas. So the difference is equivalent to amount adsorbed. So that is a straightforward. Right? How we do it? Let's see, this is the system. We have a gravimetric method, something like this. So like leave all these things. We are only interested in this one. Here what we have is a microbalance, is just like, so here we have a microbalance which is outside the system. It is not inside the system. You see, how this microbalance works is that with the magnetic effect. So magnetic levitation effect will kind of like takes care. So what we have is a gas inlet coming from here, and then we have like two holders. One is one here, one here. Two holders means nothing. We can actually use two samples to do it at one time. So it's like, it's nothing to do with anything. It's kind of like you can have two samples, same sample or different sample, it doesn't matter. So what we do is like before entering the gas, we try to measure the weight of the solid, and then we kind of like allow the gas at a given pressure and temperature, and then try to see the change in weights in the microbalance. So this is a very sophisticated system, but it will take huge amount of time to get the equilibrium. But the adsorption isotherms that we get from this system is more accurate than volumetric method, because as you see, volumetric method involves some assumptions, right? So these are the two ways we kind of get the adsorption isotherms using experiments. So the third one is grand canonical Monte Carlo simulations, right? So these are the experimental techniques. So far we discussed a couple of them. The last one we kind of like talk about is the simulation technique. So what we have to do here is that we try to kind of like build a system. So that means that when you say MOF or geolite, so we build the structure of the MOF or structure of the geolite and perform grand canonical Monte Carlo simulations. That means that what we assume here is that once the equilibrium is reached, The condition for equilibrium is, what is the condition for chemical equilibrium? Temperature should be same, pressure should be same, chemical potential is equivalent to the same. So what we do here is that we say here we have solid and here we have gas. These are the two phases and these two are in equilibrium. So then the chemical potential of gas in these two phases are equal. So the chemical potential in the gas phase is equivalent to chemical potential of component I in the solid. So that's I in this. So we apply this principle to get it. Right? How we do it? Let's see this one here. So these are the three parts. The first one is that we have to build the structure. So that's like you see a structure of a geolite, MOF or anything, right? And then we perform different moves. Like what move we do? We kind of like assume a fictitious reservoir. That means that reservoir is not there, but we assume that there is something. And then we try to kind of like pick the molecules from there, right? And then try to take a molecule like this and try to insert into the system, right? And then calculate the chemical potential of the molecules. And then compare with the chemical potential of this one, the fictitious reservoir, whatever, like we kind of like try to say, okay, our chemical potential is -5. Okay, so then we start with that and then see how many molecules can enter into the system. And then -4 and then check how many gas molecules into the system. And again this chemical potential can be related to the pressure or fugacity. So that's why we kind of like try to see. In addition to the insertion, we also do the deletion. Like it's not that we always try to insert the molecule, sometimes we delete randomly some molecules and try to compare the chemical potential of the system with the and two other things what we also do is the translation. Translation is nothing but whenever a gas molecule is here, we not only kind of like insert and delete, we also try to move it, translate it and see, because whenever we kind of like do the translation moves, the energy changes and therefore the chemical potential. So we will try to see how it affects. Other one is rotation. What we do, we take a center of mass and rotate the molecule. So why this rotation is important is that, again as I said, whenever we have a pore something like this, right? So you have CO2 molecule like, so you rotate it, maybe the oxygen will come here. When the rotation happens, again the energy changes. And again we kind of like try to calculate the energy and relate it to the chemical potential and try to again compare with the reference chemical potential. So this how, like these are the 4 different moves which we do in grand canonical Monte Carlo. One is insertion, second is deletion, third is translation, fourth is the rotation, right? So we kind of like do all these 4 mostly in grand canonical Monte Carlo simulations and get the adsorption isotherms. There is one more. This is especially we do it for MOFs or materials which are flexible. That means that when the gas molecules enters into the system not only size, shape can also change, right? It's not just the size but also the shape. So we'll kind of like take care of the system deformation using osmotic ensemble, but yeah, that depends on system to system. Usually whenever we perform grand canonical Monte Carlo, we only do this 4 moves. If required, we also have to take care of the cell deformation. Okay, this is actually very important when we deal with the bigger molecules, right? Something like this. So what happens is that when these molecules enters into the system, they try to kind of like either expand or contract. So that times we have to take care of that one. Yeah. So these are the few examples how we kind of like get the adsorption isotherms using grand canonical Monte Carlo. So it's kind of like at different pressures or like in say fugacities, we try to calculate the loading and then this. So what you can see here is that the black ones the black squares and then triangles which are in the black at 600 Kelvin and 700 Kelvin using experiments, and then the colorful ones here are from the simulations. You can see that even using simulations you are able to predict the adsorption isotherms very well, right? But still you see here and there some differences, but they are not major. You are able to predict both qualitatively and quantitatively very well. Okay, I think with this we can stop. Okay, so with this we can stop, especially we kind of like see whenever we kind of like use gravimetric method or volumetric method, both are good. Gravimetric method is more accurate, like that's why you see precision is very high, and it kind of like depends on the time and then complexity, you need to choose the method you wanted.